Today, we will be solving some problems on combustion. So, principles of combustion, material balance. Let me write problem for you. You read the problem carefully, and then we both will solve together this particular problem. So, I write the problem for you. A furnace is heated by combusting a fuel gas of composition 29% CO, 9% CO2, 16% hydrogen and 46% nitrogen. Mind you, the composition of gases is always given in volume percent unless otherwise stated. Hence, these percentage are also on volume percent. With dry air, when we say dry air, the air has a composition 79% nitrogen and 21% oxygen. The products of combustion, are analyzed with the offset apparatus, and as all of you know that whenever analysis of the products of combustion is given or is done by offset apparatus, the analysis is always on dry basis. So, this point is to be noted that offset analysis gives the analysis of POC or products of combustion on dry basis. So, as such the analysis, so the POC analysis or POC analyzes again the analysis on volume percent, 15% CO2, 7% O2 and 78% nitrogen. Calculate the following with reference to one meter cube of fuel gas measured at 1 atm and 0 degree Celsius, that is NTP, normal temperature and pressure. We have to calculate the following. A, calculate volume of POC. Now, report the volume of POC at NTP, STP and 1000 degree Celsius. Second, or B, volume of air in meter cube again at NTP. C, percent excess air, and D percentage H2O in POC. So, I give you some time, you read the problem carefully and then attempt to solve this problem with me. I hope you must have read the problem by now. Take your calculator out and begin to solve the problem with me. So, the first thing is to represent, as I said, the inputs and outputs, that is whatever is given in the problem in a box. A box, for example, representing a furnace. This particular representation and solving the problem, it is helpful in that you are writing everything which is given in the problem in the form of inputs and outputs. So, all the information which is given in the problem is before you to solve the problem. That means you do not need to read the problem all the time. So, this is the typically all material balance problems are solved this way, or you may develop your own technique to solve the problem, that is okay. So, I will be proceeding to solve the problem by reporting all the inputs and outputs in the form of a block diagram. So, this is a block diagram. So, here a fuel gas of composition, say 29% CO, 9% CO2, 16% H2 and 46% nitrogen is given to us. Now, this particular fuel gas is burnt with dry air. A dry air has a composition of 79% nitrogen and 21% oxygen. That is what is given to us. Then in the output, say we have flue gas. Note the difference between fuel gas is something which burns and the fuel gas is products of combustion. You can also write down products of combustion, or you can also write down flue gas, whatever is comfortable with you. So, flue gas, they are also called POC, and it is given say 15% CO2, 7% oxygen and 78% nitrogen, that is given to us. And we have to calculate, the first calculation that we have to do is the volume of POC. So, in order to calculate volume of POC, let us assume 1 meter cube of fuel gas, that is the basis of calculation, and this is at 0 degree Celsius and 273 and 1 atmospheric pressure. That is what given to us. Now, we have to calculate the volume of POC. Assume Y meter cube is flue gas or products of combustion which is at 1 atmosphere and 273 Kelvin. That is what we are assuming for calculation. Now, as I have said, in order to calculate the volume of flue gas or volume of products of combustion, we have to do carbon balance. So, as such, I will making the carbon balance. So, let us perform, you perform along with me, perform carbon balance. To perform carbon balance, we can write down in words, carbon in CO plus carbon in CO2, that is what is present in the fuel gas, and that should be equal to carbon in POC or flue gas. Both are the same thing. I may use this term interchangeably. So, they represent the same. You can call products of combustion or you can call flue gas. So, you have to make this particular carbon balance, since there are no losses of carbon is given in the problem. So, whatever carbon is being input, that carbon has to come out. So, if you perform this balance, now there are several ways to perform this balance. You can perform the balance on the basis of kg, kg mole or meter cube. So, I will perform on the kg mole basis, because the mole percent and volume percent, they are the same. So, I can put it now straight away 0.29 plus 0.09, that is in carbon moles in CO2, that is equal to 0.15 Y. So, straight away I get now Y, that is equal to 0.29 plus 0.09 upon 0.15, and this comes to be equal to 2.53 meter cube, and mind you, our basis was this value is at 1 atmospheric pressure and 273 Kelvin. This is also called in standard physics book NTP, normal temperature and pressure. Now, it is also being asked to calculate the volume of POC at STP. So, volume of POC at STP, volume of POC or the flue gas at STP. Now, STP represents 1 atmospheric pressure and 25 degree Celsius or 298 Kelvin. So, the volume of POC here, that will be equal to 2.53 into 298 upon 273, and that is equal to 2.765 meter cube. This volume is at 1 atm and 298 Kelvin. Now, the problem also says you report the volume of POC at 1000 degrees Celsius also and 1 atmospheric pressure. So, volume of POC at 1273 Kelvin, which is equal to 1000 degrees Celsius, and 1 atm pressure, that is equal to, so this volume will be equal to 2.53 into 1273 upon 273, and this is equal to 11.8 meter cube. This is at 1 atm and 1273 Kelvin. So, this is the answer. This is also the answer, and earlier was also the answer. So, why I asked you to calculate particularly at 1273 Kelvin is to appreciate the fact that the gases expand on heating, which all of you know. Now, you note from here that there is approximately 5 times increase in the volume of products of combustion than what it was at 0 degree Celsius and 1 atmospheric pressure. So, what does it imply? It implies that while designing the fuel fired furnaces, it is the volume of POC at that particular temperature is very important, because once you combust, the volume of POC will increase. So, accordingly the cross section area for the flow passage of the POC has to be designed. So, let us take the next, we have to find out percentage H2O, percentage H2O in POC or flue gas. It does not matter which order you calculate and which order it is given, as long as you report all what is being asked to you. So, percentage H2O is very straightforward. The reaction is H2 plus half O2, that is equal to H2O. So, straight away the percentage H2O, that will be equal to 0.16, this is the kgmole of H2 and same as H2O. Now, here we have to divide it by the total volume of POC or flue gas. So, total volume of flue gas would be dry volume plus volume of H2O. So, dry volume at 0 degree and 1 atmosphere we have determined as 2.53. To this we add 0.16, that is the volume of H2O, and if we multiply by 100, then we get percentage H2O is 5.95%. So, this is the answer. So, the offset analysis is gives on dry basis, that is what it is given. Now, the moisture content is 5.95%. Now, next we have to find out volume of air. Next we have to find out volume of, let us say, dry air. Volume of dry air. Now, in finding out the volume of dry air, as I have said, what you have to do? Do you recall from the earlier lectures on gasification or on carbonization, where I have said that if you want to determine the volume of dry air, you have to do nitrogen balance. You can argue, sir, oxygen balance can also be done, but remember oxygen is reactive. So, where it has reacted you do not know, and it is liable to commit the mistake. So, if you take nitrogen balance, then you are safe, because nitrogen is inert and it does not react with anything. So, whatever nitrogen is in, the same nitrogen will be out. So, nitrogen balance is always very safe in order to find out the amount of air. So, we will do the nitrogen balance. Now, before that, let us consider, let x meter cube is air or dry air, and we are representing at 1 atm and 273 Kelvin. So, we have to do now the nitrogen balance, and nitrogen balance is, say, nitrogen from air do not forget to add nitrogen from fuel gas, because there is a 46% nitrogen is also there in the fuel gas. So, plus nitrogen in fuel gas that is equal to, in this particular problem, nitrogen in POC. From all sources you have to consider the input, and from all sources you have to consider the output. So, if we make this particular balance now, nitrogen from air, the composition of air, 79% nitrogen and 21% is the oxygen. So, I can straight away write down 0.79x plus 0.46, that should be equal to nitrogen in POC is given say 0.78 and into 2.53. 2.53 is the volume of dry POC at NTP. So, from it straight away I can solve the value of x. The value of x would be equal to 0.78 into 2.53 minus 0.46 divided by 0.79. So, now you can just take a calculator and solve it, and the value will be coming approximately equal to 1.9176 meter cube at 180 m and 0 degree Celsius. So, that is what the volume of air in this particular, this is the answer for volume of air. Now, it is interesting to develop a field, the ratio between volume of air and volume of flue gas. So, if you find out the ratio, if you calculate for example, ratio say volume of flue gas upon volume of air, it is just to get a feel, though it is not given in the problem, because from the solution of the problem you should also analyze it and see whether you can get some feel about the ratios of different inputs and outputs. Of course, in this particular case the ratio would also depend upon what is the composition of fuel gas, but in this particular case the ratio is equal to 1.318. It is just a information which may help in some case. Now, next we have to calculate the percentage excess air. We have to calculate now percent excess air. Now, as you know, the percent excess air or excess air, that is equal to actual air minus theoretical air upon theoretical air. Or you can calculate anyway, you can also calculate actual oxygen minus theoretical oxygen divided by theoretical oxygen, because they are air and oxygen and nitrogen, they are interconnected. Say 1 mole of oxygen is equivalent to 3.76 moles of nitrogen, or 1 mole of oxygen is carried by 4.76 moles of air. So, they are all interrelated, it depends on whichever way you define, whether you define excess air by on the basis of air or on the basis of oxygen, it just becomes the same. So, we can calculate now. So, first we have to calculate theoretical air. So, because actual amount of air we have already calculated, that is 1.916 meter cube. Now, what we have to calculate is the theoretical air. Now, you recall what does it mean by theoretical air? The theoretical air always means the air required for complete combustion. That is the clear cut meaning of theoretical air or air for complete combustion. The clear cut meaning that you have to calculate the amount of air which is required for complete combustion, or the stoichiometric amount of air, all have the same meaning. So, in this particular case, if you have to calculate theoretical air, then what we have to consider? We have to consider the following reactions. The reactions are CO plus half O2, that is equal to CO2, and H2 plus half O2, that is equal to H2O. These are the two reactions which are responsible for combustion. So, straight away we see 1 mole of CO, half mole of oxygen, 1 mole of H2, half mole of oxygen, that is the theoretical oxygen. So, we can calculate now the theoretical air that will be equal to 0.29 upon 2 plus 0.16 upon 2, you have to divide by 0.21, and this is equal to 1.071 again at 0 degree Celsius and 1 atmosphere, because 1.071 of course meter cube, because the volume of gases without mentioning pressure and temperature, it has no value. So, now we can calculate the excess air. Now we can calculate excess air, and the excess air would be, we know 1.916 is the actual amount of air, minus 1.071 is the theoretical amount of air. You have to divide by 1.071, that is the theoretical air, into 100, because excess air is always referred with reference to the theoretical amount of air. So, this excess air in this particular case, it comes out to be equal to 78.89%, and that is the answer for the excess air in percent. Now, in another way, this excess air can also be calculated. Now, if you see the volume of or the offset analysis of flue gas or products of combustion, if you look, you note that products of combustion, it contains 7% oxygen. So, this 7% oxygen means it is a so called excess oxygen that is present in the flue gas, which has come from the amount of air which has been supplied. So, we can also calculate now in this way reverse. If you know the percentage of oxygen in POC, then alternatively only in this particular problem you can calculate. Had there been CO in the products of combustion, then probably different method is to be adopted. So, alternatively the excess air can be calculated from, because you have 0.07 is the percentage oxygen into 1.916 is the volume of POC. If you divide it by say 1.071 is the volume of theoretical air, you have to find out now the theoretical oxygen. So, multiplied by 0.21 and multiply by 100. So, this gives you around 78.74%. So, from both the methods we get, say in earlier method we got excess air 78.79%. Now, here we are getting 78.74%. The slight difference, that may be the analysis or round up the error. So, what I mean to say is that from both methods the excess air can be calculated, either from the products of combustion, because the excess oxygen in the products of combustion, it is due to the excess air, but when the products of combustion contains carbon monoxide also, then you have to consider the oxygen required for CO, and then you have to calculate. So, this is about this particular problem. Now, I can give you one problem so that you can solve that particular problem on your own, and this problem is self assessment problem. Self assessment problem, you have to solve yourself. I write down the problem for you. A solid fuel, for example coal, a solid fuel fired furnace is used to heat billets for deformation processing. You know, for deformation processing, you heat the billet to 1000 or 1200 degrees Celsius, so that deformation is done easily. The moisture content of the fuel of the fuel as fired is 3%. The barometer reads 735 millimeter mercury pressure. The air temperature is 20 degrees Celsius. The relative humidity of air is 45%. Mind you, here air is not dry as compared to the previous problem. Here air is humid and the relative humidity is 45%. The offset analysis of POC is 10.3% CO2, 2% CO, 6.2% oxygen and 81.5% nitrogen. The ultimate analysis of coal now you remember, as I said, the ultimate analysis is given always on the dry basis. So, the ultimate analysis of the coal is 72.5% carbon, 7.5% hydrogen, 6.7% oxygen, 1.3% nitrogen, 2.5% sulfur and 9.5% ash. I think the problem is complete. They are given a solid fuel fired furnace. Coal analysis is known. The coal when fired contained 3% moisture. The barometer reads 735 millimeter of mercury. That means it is not 760 millimeter, it is 735 millimeter. Air temperature is given, the relative humidity is given, and it is also given the saturation, the vapor pressure of air or vapor pressure of moisture at the temperature and pressure, that is the saturation vapor pressure at saturation or saturation vapor pressure that is equal to 17.54 millimeter mercury. That means the air at most can contain 17.54 millimeter mercury pressure, the amount of moisture. what you have to calculate? So, calculate per kg of coal now. For your information, the analysis of solid fuel is always given on weight percent. So, you have to calculate per kg of coal A excess air. Of course, in percent. B, you have to calculate air required. Of course, in meter cube. C, you have to calculate volume of flue gases. Volume of flue gases or products of combustion weight basis. In meter cube at NTP and STP. That is what you have to calculate. Now, as I already illustrated one problem, I straight away give you the answer. So, when you calculate, you can match. Now, in order to calculate the excess air, all of you know, first of all, you have to calculate the volume of POC. From volume of POC, you have to do the nitrogen balance, and you can find out the actual amount of air, because excess air is actual amount of air minus theoretical air upon theoretical air into 100. So, once you find out the actual amount of air, then you have to find out the theoretical amount of air as if it is required for complete combustion. If you do this, all these things, then the excess air for this problem, it comes to be, the answer for this would be 38.33% is the answer. Again, if you calculate volume of air, now remember, you have to calculate at NTP and STP. Don't forget to take into account that the air is moist. So, volume of air, that will be 13.315 meter cube at 20 degree C and 735 millimeter mercury, and it is also 11.998 meter cube at 0 degree C and 760 millimeter mercury. You can also calculate the volume at 25 degree C and 760 millimeter mercury. Well, this is just a matter of conversion. Then you have to find out the volume of flue gases. Now, remember, the volume of flue gas, as I have said earlier also, is the volume of dry volume plus H2O due to reaction between hydrogen and oxygen plus moisture of the fuel. So, if you perform, then the volume of the flue gas, it comes 12.148 meter cube at 0 degree C and 760 millimeter mercury. Now, this volume is also 13.482 meter cube at 20 degree C and 735 millimeter mercury. At all other temperatures and pressures, you can calculate this volume also. So, this is what the problem which I thought you will do yourself. Now, another problem I would like to give you is that I will partially solve and partially solve yourself. Now, the problem is as follows. In a continuous heating furnace, in a continuous heating furnace, (750 kg per hour) pulverized coal is burnt with 3% moisture, and the following ultimate analysis. Ultimate analysis. is given on wet percent. Now, in case if it is not mentioned, it is always given on wet percent. That is 77% carbon, 7% hydrogen, 4% oxygen, 1% nitrogen, 2% sulfur and 9% ash. In normal operation, the offset analysis of POC is 13% CO2, 0.5% CO, 6% O2 and 80.5% nitrogen. Now, the operator has opened the door for charging. What the operator has done? The operator has opened the door for charging. He observes that the analysis of POC is changed. So, now the offset analysis of POC is 11.5% CO2, 8.2% O2 and 80.3% nitrogen, in spite of same firing rate, and burner adjustment as was in normal operation. What he has done, he has just opened the door and he analyzes the POC by offset apparatus. He finds that the analysis is changed. He thinks that he has not changed the firing rate, he has not changed the burner adjustment, nothing he has done, but he is surprised that the analysis of POC is changed. Now, he has approached to you and he wants to clear the doubts. What he wants to know? He wants to know, sir, what has happened? What has happened on opening the door? He is surprised. He has not changed the burner adjustment. He has not changed the firing rate. Everything was similar as it was earlier. Now, he sees that the analysis has changed. So, he wants to know what has happened, sir, on opening the door. Then he also wants to know why analysis is changed. Why analysis is changed? He also would like to know why analysis changed, because now you see the analysis of POC now does not contain any amount of CO. In the normal operation it was 0.5% CO. Now there is no CO in the volume of POC. He is surprised. What has happened? So, please explain to him. Please explain to him qualitatively. You know, he is the operator, he is a very sharp person. He wants to know the figure from you. He wants to know the amount. So, please explain to him qualitatively and quantitatively as well. And quantitatively as well. You just can't escape by telling him some bullshit. You have to give him the figure that this has been happened and these are the values. So, this is what the problem before you. How would you approach to solve this problem? Now, the first of all is you note what has happened on opening the door. When he has not changed the firing rate, when he has not changed the burner adjustment, then the only thing on opening the door has happened is the amount of air has rushed into the furnace chamber. So, on opening the door, the air has rushed into the furnace chamber. So, now the furnace chamber has air from two sources, one air which has come through the opening of the door, or you can call air leaked, and another source of air that you are already supplying during the normal operation. Why analysis is changed? Now, since if you see the analysis of the products of combustion in normal operation, you will note that it contained 0.5% CO. That means combustion was not complete. You note also the combustion was not complete in spite of having 6% oxygen in the products of combustion. You recall from my earlier lectures I said that you always require excess amount of air to obtain complete combustion, and the problem says also that you have 0.5% carbon monoxide with 6% oxygen in the flue gas, that is even you are burning coal with the excess air, still the combustion is not complete, and that is the fact. So, you have to supply the excess air. So, why analysis is changed? The reason for it is in the normal operation there was insufficient amount of air. So, carbon was combusting to CO2 and CO. Now, extra amount of air is available. So, on account of air, now the combustion is complete, and on account of that you do not have any incomplete combustion product in the flue gas or in the POC, and that is what you are observing, that you have 11.5% CO2 and 8.2% of oxygen, that is whatever amount of CO was there in the normal operation, now it has disappeared. That is the answer for why analysis is changed. Now, you have explained to him, now you have to calculate the quantitatively whatever you have said to him. You have said to him two things. First, you have said to him air has leaked, so he wants to know what is the amount of air that is leaked. Then he wants to know, or what is the amount of air that is leaked, he wants to know in terms of theoretical air. So, on the quantification front, what you have to calculate, first you have to calculate when the door was opened how much amount of air has leaked into, and this air leakage you have to express in terms of theoretical air. So, again you can solve this problem with the help of the input output box or material balance. Simple material balance you have to do it. So, the first of all you have to do the carbon balance. Now, note in the carbon balance, because the coal contains sulfur and carbon, you know that the offset analysis SO2 is not separately reported. So, while doing the carbon balance you have to take carbon and sulfur both, and that is equivalent to the amount of CO2. So, I just give you the hint. So, let Y is the moles of flue gas. Now, if I do the carbon balance, then carbon balance will be on moles 0.777 divided by 12 plus 0.02 upon 32, that is equal to 0.13 plus 0.005 into Y. Now, here the basis of calculation is 1 kg coal. So, if I calculate y will be equal to 0.4802 moles of flue gas. Now, once I know when during the normal operation, now when the door was opened, I am again given with the analysis of the products of combustion. So, I can calculate now again y dash when the door was opened. So, this will be equal to 0.564 moles. So, I can find out now air leakage by doing the nitrogen balance. So, you can perform yourself. So, air leakage, now you have to find out from the nitrogen balance the air in both the cases. So, if you do that, you will get 23.51 meter cube per minute for 750 kg per hour coal. Now, you have to express this air leakage in terms of the theoretical air. What you have to do? Calculate the stoichiometric amount of oxygen or theoretical amount of oxygen by complete combustion. So, air leakage in percent theoretical air, that will be equal to 21.46%, and that is the answer, and that is the answer. And now you have satisfied the operator also feels good and you also feel good.